Next, I will use a few slides to go through how we evaluate the resulting linear regression model. Okay, a model is a tool that we use to make predictions. So we want the model to perform well. And then here comes the question of how do we measure the performance? How do we know that this is a good performance? Okay, so for linear regression, because the output variable is a continuous number, so we can simply use the differences between the actual labels of in our training data and the predicted outputs. We use the difference between them. If that difference is small, then we say this is a good model. Okay, so we write the distance in terms of we also call it an error term. Okay, if we call the error between the actual value, the actual label, and the predicted value, then we write it as EI, which is the ith instance. Okay, so if we plot the actual values in black and the predicted values in blue here, then we notice that the summation of all the errors in this form, it's always 0. Okay, because we can do the calculation if we use all the to substitute y hats into this form. We found that all the errors sum up, they always sum up to 0, and we need to come up with some different ways to measure how, overall speaking, the overall performance of the model is. Okay, so the R-square is something we define. It measures the proportion of the variance in Y that is predictable from Xi. So it's a range between 0 and 1, and a low range means that less variance explained by the model, and a higher range, a higher number means that a bigger part of the variance explained by the model. Okay, so for example, R-square equals 0.2 means that 20% of the variance in the training data is predicted by the linear model. So the R-square can be measured by the ratio of the residual sum of squares, okay, which is what's left in the predicted value. So the difference between the actual number and the predicted value raised to the power of 2, okay, and then sum them up. So in this way, we avoided the problem we mentioned before in the previous slides, that the summation of EI is always 0. Okay, so that's something we know when we define the task, when we define the cost function of linear regression, right? So it sums, if the error sums up to 0, then there's no way we use it as a overall performance. And same applies here. We use the sum of the square of errors to be the residual sum of squares. And also we have a total sum of squares, which is defined by the difference between each y and the mean values of y. This is the original variance in data. Okay, so if the data vary a lot from the mean values, then this sum of squares in total should be a higher value. Okay, so and then we use 1 minus the ratio of this term, then it is what's left, what's explained by the linear model. Okay. So there's a whole lot of techniques in statistics that plot the error terms. For example, in order to visualize how well the model is. So for example, we can plot the error terms EI, right? So although the summation of EI is not useful, But the individual EIs, if we plot them against the predicted values, it's quite useful to evaluate whether how good the model works, whether the model works equally well among all the data points. So if the EI randomly disperse along all the predicted Y hats, then the linear model is more appropriate. Okay, we want the EI to be as evenly distributed as possible. And if it's not evenly distributed, for example, in this way, then it's a so-called non-linearity problem in the model. Okay, so that's it for how to measure the residual, how to measure the performance of linear models in general. And I only go through some main points, and there are a lot of other evaluation ways in terms of describing or explaining the meanings of the coefficients in the fitted linear model, but that is the topic of statistical studies, not what we are focusing here right now.